So I'm going to start off talking about the Apollo sample request process at NASA Johnson Space Center. That's where I work, primarily in the curation of the Apollo samples, and how the curation process works with those samples for us. Provide some examples of how we actually work on the samples, and do some go into some details on some specific projects that I've worked on. So the samples themselves are stored in Building 31 North at Johnson Space Center in Houston. This building was specifically built to house the Apollo samples, so it is very secure. The samples themselves are stored on the second floor of the building. It's a two-story building, although the floors themselves are also elevated half of a story to be above any potential flooding. The walls of the building are built to be 6 cinder blocks thick. They're incredibly densely populated with extra thick rebar to be very secure against any flying debris from hurricanes and tornadoes. It is designed to stand up to rocket-propelled grenades, just in case that would ever come into it. So it is extremely secure. Officially, we can say it is rated for a Class 4 hurricane. We can't say 5, Category 5, because there is no technical upper limit to the strength of a Category 5, but any 5 that we might conceivably expect to see, this building should still be standing even if everything else is gone. And even just in case there was some massive catastrophe and the building was wiped out, we also keep a representative 15% of the Apollo collection in a remote storage site that is, in fact, even more secure than this in New Mexico. But it is not for any kind of work or processing in there. It's simply a small storage site. So over here we have Apollo 12 astronaut Alan Bean collecting samples on the lunar surface, and in particular there he is collecting a core sample being drilled out of the lunar surface. And I'm going to talk a little bit more about a core sample similar to this one a little bit later. So the general request process for getting samples from NASA starts with contacting our lunar curator, Ryan Zeigler. And he's the first person that requests are sent out. Samples can be requested for research, education, and public display, and almost anybody is welcome to submit requests to him. Processes and requirements are described on the website. These requests that are submitted get reviewed by an independent research board called the AARB, or Astro Materials Allocation Review Board. And that board is independent of NASA. It's comprised of scientists in the lunar science field who have a great deal of experience working with lunar samples, and knowledge of the samples, knowledge of scientific techniques and instrumentation. So they have a good idea of how to understand the requests that are submitted in order to determine their validity or lack thereof. Then they make recommendations of which of those requests should be passed twice per year, send those to NASA headquarters, and NASA headquarters makes the final decisions on which samples get approved for allocation. Once approval is made, then our curator oversees that allocation process, which basically means he tells me and a couple of other people what to do. And so we're the ones who do the actual preparation and processing of the samples in order to fill the allocation needs. And anything that is left over after the research is completed or after the education outreach event is completed, all of the material has to be returned to us afterwards. It is only a loan, and our department can recall the material at any time. Usually we work with people to make sure that they're able to complete whatever their they got the samples for it, but occasionally we do have to recall them. So here's some images of the inside of the pristine Apollo sample laboratory vault. Pristine has a specific definition in our case. It means the samples have not been exposed to Earth's atmosphere at all since they were returned to our facility. And so the large image on the left is the interior of our sample processing lab. It's filled with nitrogen cabinets, so the samples themselves are processed under nitrogen and stored under nitrogen as well for the most part. When they were originally brought back, they were worked under vacuum systems instead, partly because they weren't sure if the samples might be dangerous and they didn't want anything escaping and harming the people. But it was quickly determined that they weren't directly harmful and that we could keep them a lot safer by keeping them in a pressurized nitrogen environment instead. Nitrogen is non-reactive with the samples, unlike Earth's atmosphere, which will oxidize them over time. And so, for instance, you're working in these glove box cabinets, and if you get a hole in the glove and you're working in a vacuum system, then you have atmosphere that's leaking in and contaminating the samples. Whereas if you in a pressurized environment, then you have the nitrogen that's leaking out instead, and you're able to quickly repair and replace the glove. We're also very limited in the materials that can come in contact with the samples and be present with them inside the cabinets. Only stainless steel, aluminum, and Teflon is allowed inside. And that is also the case with the samples inside the vault, which is what's shown in the image on the right. So that's a close-up of the Apollo 11 storage cabinet inside the vault. So if you look in the back of the lab, behind this white door, there's a big vault door, and it is an actual Federal Reserve Bank vault door. So behind that, there's another room that's just a little bit smaller than the processing lab here, filled with many more cabinets like this one. Each cabinet is dedicated only to a specific Apollo mission. We don't mix the missions in the different cabinets because we don't want to risk cross-contaminating the samples. Missions landed in different locations on the lunar surface with different local geology and geochemistry. And if we got a little bit of dust from one sample onto another one, that would mess up future studies. So this here is our display cabinet, which is visible from a viewing room on the side of the sample laboratory. And this breaks that rule I just told you about mixing emissions in the cabinet. So there's 5 samples on display in here from Apollos 15, 16, and 17. These are representative of the different rock types that are found on the surface of the moon. This is also the largest display of lunar material anywhere in the world by mass. So these, now it does break that rule of mixing emissions, however, we would never process samples in this cabinet. This is only for display purposes. When we bring tours up into that room to look in, then it's very convenient for them to look at the samples. We can describe them to them in a tour. If we needed to do any processing on one of these samples, it would have to be packaged up and transferred out of the cabinet for an airlock and into an appropriate processing cabinet for its mission. Now, I could go into a lot of detail, tell stories about each one of these rocks. In the interest of time, I'll pass over that for you. If you ever come to Johnson Space Center for a tour, you'll get to hear a lot more about them. So here is kind of a special circumstance from last year. This is me in blue hat. When I was actually processing a lunar sample. This was Apollo 17 basalt, volcanic rock, that was kept in frozen storage ever since it was returned to NASA and left unstudied. NASA did retain a subset of the Apollo samples and left them completely unstudied, intentionally to save them for future generations when new technology would be available to better take advantage of them and would benefit from having fresh, unstudied carbon samples. And this sample was finally approved for study and allocation, and it was kept at negative 20 degrees Celsius the entire time. And as part of the requirements for processing and allocation, it had to stay at negative 20 during the processing and allocation process. So we had to set up a temporary facility inside of a large walk-in freezer with a nitrogen cabinet. So here I am working inside there wearing cold weather gear, underneath clean room garb, and so that is the original rock as I was documenting it before processing on it. Here it is after I performed the first break on the rock. And here's the interior, fresh interior surface of the rock. That's this piece right here. The interior surfaces are of particular interest to a lot of researchers. So there's a lot of documentation that goes on with all of the processing that we do. More time is spent documenting and recording what we do in our database than actually handling processing the samples themselves. So here's actually where I spend the majority of my time. The polymer thin section lab, which is primarily run on and working. So this is where I make thin sections, which are essentially microscope slides of rocks. And most of the time I'm making them about 35 microns thick, which is less than half the thickness of hair on your head. The reason for that is at approximately that thickness, the optical properties of the rock allow light to pass through it, and they bend the light to create colors and patterns that are very indicative of the individual minerals that are present within the rock, and it allows for identification and classification of rocks. So working in here involves a lot of epoxy mixing and use, so that's done in the fume hood here, and then a lot of polishing. We also never expose the samples to water during the polishing and cutting processes. Instead, we use ethanol because it doesn't react with the samples. So here's the process of making sections. It begins with making potted butts, as they're called, which is a chip of rock that's encased in a plug of epoxy. I'm not exactly sure where that term comes from, potted butts. I think it's British, or at least it sounds like it. But yes, so chips of rock are produced up in the lab that I showed you before, and then they're transferred into this thin section lab. They're placed inside molds. They're opened up, so they're no longer considered pristine because they're exposed to the air at this point. And then I mix liquid epoxy and pour it over top of them inside the molds, orient the chips so that the face that I want the section is facing downward. And then remove the potted butts from the mold, carefully grind and polish the surface of that to a 1 micron finish, and then use another thin layer of epoxy to mount those potted butts to slides, which I then cut off with a low-speed circular isomet saw, as we call it, with a very, very thin lapidary blade. And I'm cutting less than 1 millimeter away from the surface of the slide in order to preserve as much of the material as possible. And then after that, the slide itself, the sample on there, is further ground and polished down to the desired final thickness and surface polish. The same can also be done with individual dust grains, as seen here, there's a whole bunch of different grain mounts, as we call it. But what do we do when the slides are finished? What are they used for? Well, one thing is optical microscopy. So we look at them under a microscope. Here is an Apollo 11 basalt. So another igneous volcanic rock that was collected by Neil Armstrong. And this is being shown here in the reflected light, so the light is being shown directly down and it reflects off of the sample directly back up. It's in black and white. And this is particularly useful for me during the thin section making process because it readily reveals any scratches that are present at the surface that still need to be polished out. But it's also useful for researchers and students to look at to determine grain boundaries, mineral textures, formation of this block. You can also, however, instead of using reflected light, you can use transmitted light. And so here we have an image of the same rock in plain polarized light. So the light is being shown, it's shining from below the sample, passing up through it, first through a single polarizer. So it's polarized light that's passing through the rock. And it starts to show a little bit of a hint of color in some of the minerals, but only a little bit. Some minerals will show more than others in this circumstance. But also some of them are completely opaque to light, even at this very thin thickness. So they show up as black. This also aids in classification of minerals. And finally, we can look at it in cross-polarized light. And this is the prettiest way to look at it. So the way that works is you are using two polarizers that are actually perpendicular to each other. Usually, if you're trying to pass light through perpendicular polarizers, none of it's going to get through. However, when you have the section in between the two polarizers, the minerals that are present within it act as prisms, and they bend the light enough that some of the light gets through the top polarizer and creates these magnificent colors and texture patterns that you can see. And the different colors and patterns that you see are specific to the type, to whichever mineral it is that you're looking at. Like the reds and blues that you see there are a mineral called olivine. Another special project that I worked on in the lab was another sample that was left completely sealed and unopened until just a few years ago. And this was one of those drive cores that this was collected on, Apollo 17 by astronaut Jack Schmitt. And it was finally approved for analysis, and it was extruded into a dissection plate. And my colleague Curation will talk more about this as well. She was the one who did the dissection on that sample, that core. It was extruded sideways into a plate, and then she dissected down about 3/4 of the way down. And then the remaining 25 to 27% that was left in the plate was delivered to me like this in the thin section lab, where it was my job to turn it into potted buds to make sections out of, which required me to impregnate it with epoxy as the terminology goes. That process is completely different than how we normally make thin sections in potted buds, because the fine-grained texture of this regolith is such that our normal epoxy wouldn't be able to penetrate through it before it starts to harden. And so the process for doing it had been developed decades ago, but it hadn't actually been done since then. And most of the equipment for doing it was no longer usable. It had deteriorated in condition so much that we had to rebuild the entire vacuum pump apparatus for our vacuum chamber that the epoxy needs to be poured within. And the epoxy itself has to be different as well, and the chemicals for that were no longer available. So we had to develop a new epoxy mixture and process of removing it from the dissection plate safely. And that required a lot of testing using simulants, as you can see here on the right. Until I was convinced that we had the good means of doing so. And so here's the actual core then after the epoxy was poured onto it and had largely solidified. Here's after it was removed from the plate with cut epoxy spacers around it to hold it in the middle of this silicone mold. And then more epoxy was poured around it inside the mold to further encapsulate and protect And once that had finally cured, I took it out and cut it lengthwise down the middle into two pieces. And then one of those pieces was chosen to be cut up into potted butts to be mounted to long rectangular slides from sections height. So here is an image of the saw as I was cutting it off. Cutting one of the slides off of potted butts. Here are the slides right after they were cut off, and then they're still thick. And here are the slides after I finished grinding and polishing them down to their final state. And now I can show you one of those slides here. This is the same reflected light image of one of those slides. Here it is polarized light, plain polarized light, and here it is cross polarized light. Colors are a little bit dim and washed out on the screen, unfortunately. But these turned out excellent, and they've been a great inspiration for the scientific community. That makes sense. And if you look at it very up close, zoom in, this coal is filled with orange glass beads. These are from the volcanic fire fountain event that occurred near the Apollo 17 landing site in the past. And they have these beautiful swirling textures and bubbles within them. This is the largest bead that was present within the sections that I made. It's just over 0.5 millimeter in diameter, 630 microns. There are a lot of much smaller beads and fragments of this orange glass that are present as well, and a few pieces of green colored glass as well. Here's a few other pictures of some recent sections that I've made. So this one, color's a little bit washed out here again, but this is green glass that's present on the outside of this sample. This one is just riddled with beautiful pink spinel crystals. You look at the moon rocks in a macroscopic sense, and they're pretty much all various shades of gray. But you look at them up close, and there's a lot of color and variation, beauty to be seen. And then over here on the right, this is a really interesting particle that was mostly metal on the inside. It's an iron nickel metal. And it's surrounded by bits of silicate rock material, and has these super fine-grained dendrites of just metal veins permeating throughout. I think the metal was probably in a molten state, and it was dropped in this silicate material. It was kind of flowing throughout all the different cracks as it solidified. All right, so I'll just sum up and say that the Astro Materials Curation Department at Johnson Space Center goes to great lengths to preserve and protect the Apollo sample collection. After more than 50 years, demand is still very robust for research, education. We still allocate well over 500 samples per year on a good year, sometimes more than that, especially lately. And a great deal of vetting and work goes into processing these samples in order to preserve the majority of them for future use. NASA is required to provide these samples for scientific use, and so we have to be very careful in how we process them in order to preserve as much material as possible. And 80% of the collection, the entire Apollo collection of 842 pounds originally, is still considered pristine, has not been exposed to its atmosphere, and is still within our control. And most of the rest has been returned to us after studies. Only a small portion of it has been destroyed over time, which was necessary as part of the liquid studies, dissolving it in acid, vaporizing it with the lasers and things like this. But all of that work goes towards informing what we're going to do in the future, including with the Artemis program. Studying these samples is what has allowed them to select their landing site for Artemis 3, which is going to be near the South Pole of the Moon, because they believe that is going to tell us provide the next bits and pieces into understanding further the history of the moon's formation. So I guess I'll leave it right now.